I welcome you all for this presentation. In this presentation, we are going to discuss about finite fields. This finite fields plays a vital role in the cryptographic algorithms. So we are discussing this finite fields in this presentation. So this is the overview of this presentation. We are going to discuss about group, ring, field, then the relationship between group, ring and field. Then another thing is the important thing is Galois fields. This finite field only we are calling it as Galois field, the inventor of this finite field. Then polynomial arithmetic, then computational considerations followed by generator. So group, I think group, ring and field somehow you have studied in the discrete structures. At least group you are very much familiar about. So group means it is set S of elements or numbers, and this group must be finite or infinite. And we are just performing some operation with this set of elements or numbers. So some operation in the sense we are representing it as a dot. So G group equal to S, that is set of elements comma dot operator. And this group obeys the CAIN property. What does CAIN means? Closure, associative law, identity and inverses. So closure is AB in S, then A dot B in S. If you are having two elements, then the operation, whatever operation you are performing with respect to the two elements, that result is also in the set S. That is the closure property. Next is associative law, that is A dot B dot C equal to A dot B dot C. The bracket parenthesis only differs. Then identity it is E dot A equal to A dot E equal to A. And inverses is A inverse, that is A dot A inverse equal to E. And commutative is A dot B equal to B dot A. Then forms an abelian group. So if the CAN property is followed, then it is called as group. And in addition to the CAN plus commutative, then it is called as abelian group. So this is the difference between group and abelian group. Next is a cyclic group. Here it just defines the exponentiation as repeated application of operator. That is, example for that is A cube equal to A into A into A. And the identity what we are mentioning, E equal to A power 0. So exponentiation A power 0, A power 1, A square, A cube, A power 4. Likewise it goes on. This is the exponentiation. So a group is cyclic. When we are telling a group is cyclic means if every element is a power of some fixed element A, then only we are calling the group as a cyclic group. So B equal to A power K. That is for some A and every B in group. Then A is said to be the generator of the group. The last topic is about generator. So this exponentiation only we are calling it as the generator. Next is a ring. Ring is also a set of numbers only with two operations. There we have only one operation. Here we are having two operations, addition and multiplication, which form an abelian group with addition operation and multiplication has closure, associativity and distributive over addition. A group has closure property, associative property, but distributive is not there. But ring has distributive property as well with respect to addition. That is A into B plus C equal to AB plus AC. And if multiplication operation is commutative, it forms a commutative ring. And if multiplication operation has an identity and there is no zero divisors, then it forms an integral domain. So what is a commutative ring? Ring and integral domain. Three terms we have discussed here. Next is about field. Field is also a set of numbers. Here also we are having two operations. One is abelian group for addition. Next is abelian group for multiplication. There we are ignoring the zero. Then we have to follow whatever the things we are following for the ring. So we can have a hierarchy with more axioms or laws, that is group, then ring, then field. So group is inside, then field, then ring and field. Group, then ring and field. So this way we are having the relationship. So here you can see the relationship between group, ring and field. So this pictorial representation, if you have it in mind, then there is no confusion between these different terms. So group means we are having four properties: closure under addition, associativity of addition, additive identity, then additive inverse. Then with group plus commutativity of addition, we are calling it as abelian group. Then abelian group with these three properties, that is closure under multiplication, then associativity of multiplication, then distributive clause, we are calling it as ring. Then commutativity of multiplication, we are calling it as commutative ring. Then multiplicative identity and no zero divisors, we are calling it as integral domain. Then multiplicative inverse, integral domain plus multiplicative inverse, we are calling it as field. So this relationship we have to keep it in mind. Next is the finite or Galois fields. This finite fields plays a key role in cryptography. Already I told you this. And it can show the number of elements in a finite field must be a power of a prime p power n. So in most of the cryptographic algorithms, the prime numbers plays a vital role, and not small prime numbers, large prime numbers. So later on in the algorithms, we will discuss what is the advantage of using or having the prime numbers in the cryptographic algorithms. So here the prime p power n, this is known as the Galois field. So always we are denoting as GF of p power n. And here we are having two different versions, that is GF of p and GF of 2 power n. These are the two most important Galois fields we are using in most of the algorithms. So first is GF of p. Here what is p? It is a prime. So GF of p is the set of integers, that is 0, 1 up to p minus 1 with arithmetic operations modulo prime p, and these form a finite field. Finite field in the sense it has multiplicative inverses, and how we are finding out the inverse means using extended Euclidean algorithm. So here this arithmetic is well behaved and can do addition, subtraction, multiplication and division without leaving the field GF of p. Let us see one example. Here you see GF of 7, that is 7 is a prime number, right? What is a prime number? It divides itself and 1, that is a prime number. So 7 is a prime number. So here with respect to multiplication, 0, we already have seen what are the list of numbers we are having: 0, 1 up to p minus 1. Here p is 7, so 7 minus 1 is 6. So only we are having the number 0, 1 up to 6. Here also 0, 1 to 6. Then we have to perform multiplication. Mod 7 we have to apply. This is very, very important. Always whatever the operation we are performing, mod 7 we have to apply. See here, 2 into 6 is 12. So 12 mod 7 is 5. So this way we have to do for all the numbers. Next is a polynomial arithmetic. So this polynomial arithmetic can come, we are using operation with respect to the polynomials. So the polynomials must be of the form f of x equal to a n x power n plus a n minus 1 x power n minus 1 plus a1x plus a naught equal to summation ai xi. So we have to note that we are not interested in any specific value of x, which is known as indeterminate. And we are having several alternatives here, like ordinary polynomial arithmetic, polynomial arithmetic with the coefficients mod p, then polynomial arithmetic with the coefficients mod p, and polynomials mod mx. So different operations we are having here. Then coming to the ordinary polynomial arithmetic, we have to add or subtract the corresponding coefficients, then multiply all terms with each other. Example is f of x equal to x cube plus x square plus 2 and g of x equal to x square plus x plus 1. So we can perform addition, x cube plus x square plus 0x plus 2. And g of x is x square minus x plus 1. So if you perform addition, 3, 0 minus 1 is minus 1x only. And x square plus x square is 2x square plus x cube. So here we are getting this value. Likewise, we can perform subtraction as well as multiplication. If time permits, you try to work out and check whether the answer is correct. Next is polynomial arithmetic with modulo coefficient. So when computing the value of each coefficient, we do some calculation modulo some value. and it forms the polynomial ring. So always the modulo must be modulo any prime number. Here we are mainly interested in mod 2. So if it is mod 2, we are having two values 0 and 1. So f of x equal to x cube plus x square and g of x equal to x square plus x plus 1. And if you want to perform addition, what we need to do is we have to consider that is we are having the value, that is x cube, it is 1, x square 1, then x no value 0, and the unit also 0. Then coming to g of x, we are having x cube no value, so 0, x square we are having 1, x we are having 1, and 1 also we are having. Here we have to perform XOR operation. What is XOR operation? It is a odd function. If you are having odd number of ones, then the output is 1, otherwise it is 0. So here odd number of 1, so 1, odd number of 1, even number, so it is 0, odd number of 1, so 1. So what is the answer if you expand to that polynomial format? X cube plus x plus 1. See here, x cube plus x plus 1. Similarly, you have to do for the multiplication. There we have to perform shift operation. Next is polynomial division. This polynomial division is similar to that of the general division only. That is how we used to write the division operation, dividend equal to quotient into divisor plus the remainder. Same only here also we are writing f of x is the dividend, q of x is the quotient, g of x is the divisor, then r of x. So we can interpret r of x as being a remainder. So r of x is f of x mod g of x. And if there is no remainder, then we can say that g of x divides f of x. What is the meaning? That is f of x divided by g of x. If it is this and no remainder, then we can write g of x divides f of x. Already this one we have discussed in the number theory presentation. So you please recall that. And if g of x has no divisors other than itself and 1, then we are calling it as a irreducible or prime polynomial. It is very, very important, irreducible or prime polynomial. An arithmetic modulo and irreducible polynomial forms a field. So this is about the polynomial addition. Next is polynomial GCD, that is we can find the greatest common divisor for polynomials, that is C of x equal to GCD of A of x comma B of x if C of x is the polynomial of greatest degree which divides both A of x and B of x. And here in order to find out the GCD of two numbers or two polynomials, we can use the Euclid's algorithm or Euclidean algorithm, both are same only. So Euclid we are passing whatever the polynomials we are going to find the GCD, and if B of x equal to 0, then we are returning A of x, else we are returning the Euclid of B of x comma A of x mod B of x. The same algorithm only, whatever we discussed to find the GCD of two numbers. So here this is the polynomial arithmetic Galois field of 2 power 3. So the addition, how we discussed there, the same thing only used here, the addition. So here 2 power 3. What is 2 power 3? It is 8. So we have to give the number 0 to 7. So only here we are having 3. So 3, so 3 bits are there. So 0, 0 up to 1, 1, 1 we are giving. And parallelly we are performing the operation. Whatever we discussed earlier, the same way only we are performing the addition operation as well as the multiplication operation. If time permits, try to work out and check whether you are getting the correct answers. Next is some of the computational considerations in this polynomial arithmetic. Since coefficients are 0 or 1, we can represent any such polynomial as a bit stream. And addition becomes XOR of these bit streams and multiplication is shift and XOR. That is the longhand multiplication we are performing. Then we can perform modulo reduction by repeatedly substituting the highest power with the remainder of the irreducible polynomial, that is shift and XOR only here also. So these are some of the examples. In g of 2 power 3 we have this value. So 1, x term is not there, so it is 0, and x square 1. So x square x1, all the terms are available, so 1, 1, 1. And if you are performing the XOR operation, we are getting this answer. See here for multiplication, x into x plus 1 into x square plus 1, x into x square plus 1, then 1 into x square plus 1. So we are getting a value like this, and we are writing that x cube plus x square plus x plus 1. So with respect to the binary format also, we can perform using shift and XOR. So the modulo reduction also we can perform, that is modulo reduction q of x, the quotient as well as the remainder we have to get it. Here also we have to perform the XOR operation. So next is the generator. It is the equivalent definition of the finite field only. Already we have seen that exponential part, right? So the generator G is an element whose powers generate all non-zero elements in F, and we have 0, G power 0, G power 1 up to G power Q minus 2. And here we can create generator from root of the irreducible polynomial. You already know what is the irreducible polynomial. Then we can implement multiplication by adding exponents of the generator. So in this presentation we discuss about group, then ring, field, then relationship between this group, ring and field, then Galois fields or finite fields, then polynomial arithmetic, then computational considerations and generator. Thank you.